All right, so welcome to another exciting episode of AP Chemistry here at Spain Park. Today is Wednesday, April the 10th, 2024. We have less than 1 month before the AP exam, before we are finished with this course. If any of y'all have any friends that are in AP Bio right now, or in AP Physics as a junior, and you would love to try to convince them to take AP Chemistry, I would love to have 5 to 6 more students sign up. Okay? Okay? Why? Because that would give me enough to have 2 sections of AP versus 1. And so for next year, 1 large one, I would like to have 2 medium-sized ones versus 1 large one. But anyway, it's also because you shouldn't even ask why. You should say because it's such an awesome class and you're learning so much that because you're their friend, you don't want them to miss out on the experience.
And when there's 2 sections, it helps everybody else by giving more options for fitting in my schedule.
That's exactly right.
Like last year, I couldn't fit in my schedule, so I had to take it this year.
Okay, so there's all kinds of good reasons. So be a friend, get them to sign up. All right, if I'm looking at my curve, all right, now let's focus. Here we go. So let's focus. So now, if I'm looking at this, first off, is this going to be a weak acid or a strong acid? A weak acid. So I know that the weak acid is in the flask at the bottom. It's not in the burette, because that's what I'm always going to be measuring the pH of. So because the pH is down here, I know it's the acid in the flask. And because it's a pH somewhere between 2 and 3, I know it's a weak acid. Okay? Because it's a weak acid and NaOH is what type of base? Strong base. I know that the pH is going to be below 7, above 7, at 7. Above 7, because the salt is going to be a basic salt. So now when I look, where is my equivalence point going to be? Where is the equivalence point?
A little bit above, like 7.
Well, how do you know where it's going to be? Halfway in the tall vertical part. So it's going to be somewhere about right there. Okay? So you go here, here's my equivalence point, and so we can see that if I'm going to just kind of be guessing, it's somewhere in that range. Okay? So my pH somewhere 8.8, guessing some range. Now, where's my half equivalence point? Half of it is halfway between. This is my equivalence point. So again, when I come down here, this is the number of milliliters. So this is where MAVA is equal to MBVB. That's how I figure out. I would know exactly the volume of the base that it took to neutralize. Okay? Now, my half equivalence point then is going to be right here. This is the half equivalence point. What is true? So if I say this, then what is going to be my approximate pKa? What's the pKa of this weak acid going to be?
Like 3.
Okay, so how do we know that?
pH equals pKa.
Because here, pH is equal to pKa. So it's going to be, I would even just guesstimate here, we'll just call it 10 to the minus 4th. Okay? At the half equivalence point. So I can estimate the value of Ka based upon the pH at the half equivalence point. Okay? Now, the thing that I've been forgetting to share is, number 1, this is the equivalence point. But sometimes you'll hear the term end point. The end point is when the indicator changes color. Okay, that's when we stop. You know, when we saw faint pink is when we stopped. When in our other titration, when we saw the faint red, reddish brown, that was our end point. Okay? Well, so the end point, so we just write that down somewhere. The end point is when the indicator changes color. The goal of a titration is to get the equivalence point and the end point to be as close to one another as possible. So we have to pick an indicator. The end point is when the indicator changes color. You want the end point and equivalence point to be as close to one another as possible. Which means you need to pick an indicator that changes color very close to the pH at the equivalence point. Now, I want to say all, I'm going to say most all, I'm not sure it's for sure all, but all the ones I know of, indicators are weak acids. And you push them one way when you have, it's Le Chatelier's principle, when you have a certain amount of H plus, based upon their Kas, you have a certain amount of H plus, it's going to be on one side, then you keep adding OH minus, and then it's going to shift it to the other side, and it's going to change colors. So to pick the indicator, that is best for a certain titration, you want the pKa of the indicator to be closest to the pH at the equivalence point. So the indicator, the best indicator, is the pKa of the indicator is close to the pH at the equivalence point. That's how you know which indicator to pick.
It's the pH of the acid.
No, pH at the equivalence point. So where you're like this one would be 8.8.
And that's the pH of the acids.
That's the pH of the solution. Now, there's really no acid left. It's now just going to be the salt. But the pH of the solution at the equivalence point, as you're going through, okay? So where MAVA equals MBVB, you want, that's where you want, whatever the pH is at that point, you want
I'll make sure we go to practice. So I look at the break of thousand practice. Okay, bro. Who lives up for
okay.
Bro, we should saving it. Good boy.
So let's look at 2015. It's like 3 or 4 pages in.
Oh, really?
Okay, so this is 15. This was an actual, obviously on the released exam that you can actually find this problem online. Okay, but I just want to focus on part C, right here. Okay. Now, the pH at the equivalence point of the titration is measured to be 2.54. Which of the following indicators would be best choice for determining the endpoint of the titration. Okay, so again, notice you're using the term endpoint. That's when it's going to change colors. We want it to change colors close to the equivalence point. So which one do you think is going to be the best one here? Thymal blue. Okay, thymal blue, because it's going to have the pKa of the indicator is closest to the pH. Okay? So it's going to change colors closest to 2.54. Now, I'm going to read the question here, and so it says, potassium sorbate, molar mass 150, is commonly added to diet soft drinks as a preservative. A stock solution of potassium sorbate of known concentration must be prepared. A student titrates 45 milliliters of the stock solution with 0.125 molar HCl using both an indicator and pH meter. The value of Ka for sorbic acid is given as 1.7 times 10 to the minus 5. So D, without doing anything else, calculate the pH at the half equivalence point. D, just calculate the pH at the half equivalence point. You don't need to know A and B or C in order to be able to do D. Now this would be a long question, so there'd be a whole lot more parts after this, but this is the only acid-based part of the question. But, are we done?
Yeah.
How do we find the pH? pH equals pKa, right? At the half equivalence point. That's all you have to know. pH equals pKa. So you take the negative log of the Ka, the negative log of 1.7 times 10 to the minus 5, and it comes out to 4.8. Okay? That's all you gotta do. You have to know that this is the one I bet you $20 on, I think.
Is it only at the half?
Only at the half equivalence point.
And then.
That's when you have a 50-50 buffer, so the two concentrations cancel out. So H plus is equal to Ka, so pH equals pKa.
And then equivalence point is.
At the
MA.
equivalence point, MAVA equals MBVB. That's the only time that's true.
You can't calculate pH with Ka.
No, that's it, because it's just because there's no acid left, you have to use the salt. That's kind of what we talked about yesterday that you missed out on. I guess we didn't care enough about you, the video yesterday.
No. I have 3 people. I got half of it.
Nobody said anything yesterday to make me think about it. Okay, so now, let's think about A. I want you to try to do A right here. Just because this is a good one. Notice it says net ionic. go ahead and see if you do B as well. And you got all that space below it, so you don't necessarily have to cram it into the space, little space that's given for B. But all that, there should be enough space. I'm just always amazed at the food variety that shows up in this class.
That's really.
Meanwhile, I'm starving.
You want some? I think so. We do. It's from India.
No,
It's Nigerian, but it's poison.
I already thought they were originally imported.
Yeah.
Yeah, I do like that.
Roll.
They have it salted.
No, it's like you can try it.
I like that salted. I like the ones that aren't
I'm not
salted.
trying to get you kidneys from this.
As much Diet Mountain Dew as I drink, my kidneys are good. As they say that Diet Mountain Dew is bad, producing kidney stones. All right, these should not be 30-minute questions for just doing A and B. All right, so when I'm looking at A, and I want the net ionic equation, net ionic, which element up here can I pretty much know is a spectator? Okay? First off, which is the acid, which is the base? Hopefully you recognize that as the strong acid, which then by process of elimination tells me that's gonna be my weak base. And in a strong acid, what do we know about the dissociation? 100%, okay? So I know that, and then which other ion is always gonna be a spectator ion? Somebody said it already. Well, the Cl, but we talked about that one, but
The K.
The K. So my spectator ions are really gonna be this and that, which is gonna make that minus. Y'all seeing that? Now, if you wanna do the whole thing, we can do the whole thing, K, C6, H7, O2, plus HCl. Now, how do you know what it's gonna do just looking at like this? Double replacement, positive, negative, okay? Another thing we can do is I know this is an acid. They're titrating it, it's pH, this is Ka, this is telling me all these clues about that it's acid and base. We memorized that HCl is a strong acid, this must be acting like the base. What do bases do with hydrogens? They accept them. Acids donate them. So this is donating to here, but it's got to have a place. So, but again, my spectator ions, I know that that's a spectator ion. That's a minus. Alkali metals are going to be spectator ions. When we're doing net ionic, AP very rarely wants the whole equation. They almost always want the net ionic. So that means that that H is going to come here, and I'm going to get H, C6, H7, O2, plus, it'd be Cl minus, but this is going to be dissociated here, so it's just going to be H plus, so it's really not going to be anything. It's just going to be that.
Put aqueous at the end on that.
Now you can, okay, they're all aqueous, but states are never required. States are never required. The total would have KCl at the end, yes. It's a double replacement reaction. And just for the record too, and we're gonna talk about this in our last unit, assuming we ever get there, okay? That double replacement is the only one where oxidation states don't change. It's the only one that is not a redox reaction. A redox reaction is where oxidation numbers change from reactants to products. Composition, decomposition, single replacement, combustion of a hydrocarbon. Anytime you make a pure element, the oxidation states always change. Double replacement are the only ones that it doesn't, that it's not a redox reaction.
And
So
is
how
it-
do we do, so what?
Is it not the back and forth arrows only when it's a strong acid or strong base?
Well, you can do both, it would definitely be that. But, you would not get penalized for not having an equilibrium arrow either. All right, so how do we do B?
M A B A M B B.
This is how do we reach the equivalence point. That's my key. That's what I'm gonna know. I'm gonna use MAVA is equal to MBVB. Okay? Now what's the molarity of the acid?
1.25 more.
1.25. I have to know that this is my acid. What volume of acid got used? And you can leave it in milliliters because it's a ratio. If this is in milliliters, this will be in milliliters. They just have to be the same. They don't have to be liters. So if you divide this by 1,000 and that by 1,000, you get the same ratio. Okay? So we're gonna say 1.25 molar times 29.95 milliliters is equal to, what's the molarity of the base?
With no milliliters.
Well, we have to understand, what do brackets mean? Concentration, that means, that's my unknown, that's my molarity of the base is what I'm looking for. And we had to identify it's the base from our equation. Process of elimination, if you know the acid, the other one's the base. Okay, so the molarity of the base is what I'm looking for. What's the volume of the base?
45.
You have to go back and read. On the mock exam, on that problem, the titration problem, students used the wrong volumes because they didn't read carefully of which one was which. Okay, so make sure you're reading carefully and going back. So this is your 45 milliliters. Okay, now I have, what am I given here? 1.25, 29.95. If this were a sig fig question, how many sig figs should be my answer?
3.
3. Notice they're reading the burette to 2 decimal places. Okay, and that was actually a question on the mock exam that most of y'all got right. Okay, so this ABCD is a pretty straightforward acid base. You can do that. So I brought this question out because of C. Because I want to stress the point that you can determine the indicator just by making it close to the pH. So again, even if you're just guesstimating and you don't know what the pH is at the equivalence point exactly, you can know that if it's strong, it's gonna be around 7. If it's a strong acid with a weak base, then I know it's gonna be an acidic salt. So there's going to be below 7, so you want to have a pKa of the indicator somewhere below 7. You know, like a 5 or a 3. And then if it's a weak acid, strong base, it's a basic salt, so I know my pH at the equivalence point is going to be above 7. So I'm going to want to find something with a pKa around 9, 10, whatever, something above 7. Okay? And there's one more in this packet that I don't want to go over. I'm going to let you look at it and do that as we go through and practice. But they show up multiple choice questions as well. But that's just, hey, I have to know that. There's no real math. You just kind of look, pH equals pKa at the equivalence point. You got to match them up.
How should we word it? This is justified?
Justify your answer means that because the pKa is 2, that means it will change colors. The end point will be close to 2, which is closest to the equivalence point, which is ideal for an indicator. Okay, you just need to make this statement that the pKa of the indicator is closest to the pH at the equivalent point, which means it'll change colors, which means the endpoint and equivalence point will be close. So does everybody understand the difference between endpoint and equivalence point? The equivalence point is this mathematical 29.95 milliliters is when MAVA, so you put 45 milliliters into the flask of your stock solution, and then you titrate it with the HCl that we know is 1.25 molar that's in the burette. Okay, and it takes exactly 29.95 is when the color changed. That's the end point. Okay? But, well, actually, pardon me. This is what you calculate. But it may not change colors until 31.00. That would be your endpoint when it changed color. But we want the endpoint and the equivalence point to be close to being the same. All right, so that was the two things that I keep going over missing as far as the difference between endpoint and equivalence point and how to pick the indicator. Everybody halfway at least comfortable on that? Okay. Now, last concept, and then we get to just start practicing. And this is what we started yesterday, and we'll just start over again today. Structure versus strength of acids. Okay? Structure versus strength. Now we have two types of acids. Okay? And I'm going to have to add in one thing here on binary. So we have a binary acid, and what do we remember that a binary acid is? It's just H and X. Now, that can still be H2S. Listen, it can be H2S, it can be H2SE. So it doesn't mean just, two atoms. It just means two different types. So it's H plus some monatomic ion. Okay? It doesn't always have to be on me. I'm narcissistic, but it doesn't. But yeah. Okay? Hey, but check out the shirt. So, okay. So in a binary acid, the strength of the acid is inversely proportional to, and we don't need to write this down, but I'm just saying it. The strength of the acid is inversely proportional to the strength of the bond. The weaker the bond, the stronger the acid. Because what makes an acid strong? If it ionizes, okay? Now again, small difference in the term. Ionic compounds, the ions are already formed, they just break apart from one another, so we say it dissociates. But an acid is a covalent compound that's sharing electrons. But when it goes into the water forces it to break apart, it ionizes in the water. So the ions get formed by placing it in the water. Now, again, small semantical difference between dissociation and ionization, but acids ionize in water. Okay? Ionic compounds dissociate in water. Just little terminology. You wouldn't lose points for either one saying anything wrong, but just might as well learn it right. Okay, so there are two things. Okay? Within a period, pardon me, not within a period, within a group. So, sorry. Within a group, the strength of the acid increases with the size of the anion, the X minus. Longer bond length, is easier to break. Okay? The longer the bond length, long distance relationships are hard to maintain. The farther apart they are, the easier it is to break them apart. Okay? So going down in a period, I keep saying period, going down in a group, fluorine, bromine, iodine. We exclude acetine because it's radioactive, so nobody likes to play with it. Okay? So going down, it's getting bigger. Electron clouds, another electron cloud's getting bigger. So that means the hydrogen's farther away from the nucleus, so it's attracting it to it. So that bond length is long, and so it's easy to break. So even though HCl, HBr, and HI are all considered strong acids, 100% ionized, HI is actually the strongest of the three. Now, how do they do that? Well, what they do is they put them into something other than water. They put them into a weak acid. They put them into something that doesn't really want a hydrogen, but they force the weak acid to become a base because it's with a stronger acid. And then whichever one ionizes the most in the weak acid, they can differentiate the strengths. For us, it's irrelevant. That's really all my information. Just kind of throw it out there for you. Okay? All you need to know is within a group going down, as the bond length gets bigger, the bond gets weaker, it's easier to break a stronger acid. Now, within a period, the greater the electronegativity, man, my last class, are you guys, anybody getting hot in here?
Yes.
Yes.
Okay, good, because my last class, they made me turn the air up, they said it was cold.
It's cold.
It's still cold.
Yeah, Alex doesn't matter.
Okay, I'm trying to be positive here. Look, I'm going uphill. The greater the electronegativity of the anion, okay, the more polar the HX bond, and the more ionizable, is that spelled right? Yes. More ionizable the H plus is. That's a lot of words. So Madeline just chooses to take a picture.
That's the real Madeline.
Although when you write it down, it sticks in the brain better. I'm just telling you, this is lazy millennial notes right here.
It's hard to stick on a water slide, so you know.
Support me.
Wait,
I am a baby boomer. Okay?
That's actually.
I'm a baby
We're
boomer.
not millennials.
Oh, you're Gen like.
Millennials.
You're past the. I think you're back to AA.
Like your son would be a millennial.
Yeah, I'm sure. Yeah, he's a classic millennial because he's 33 with no job and doesn't want to work. And so, hi son, I love you.
This doesn't know what's this.
You should tag him.
Yeah, no. Okay, so listen. So within here, so as we go down, HI is the strongest. HBr, HCl, HF is actually classified as a weak acid. So even though fluorine is mostly electronegative, the bond length is so short that it's too strong to ionize to a significant amount. Now, when you look up here on the chart, it's the Ka is 3.5 times 10 to the minus fourth. So it's one of the stronger weak acids, but it's still not 100% ionized because the bond length is too small, even though it's got the greater ionization. Greater electronegativity. When you go across though, if I'm going to compare HCl to H2S, yes, S is smaller than bigger than Cl, which means the bond length's a little bit bigger, not much, but a little bit, okay? But the electronegativity is what we look at going left to right. Since chlorine is more electronegative, that makes the bond more polar, makes the hydrogen more positive, more vulnerable, more ionizable, and so the water can pull it off more easily. So going left to right, the acids get stronger.
So it gets stronger like
So, right, so this is your strongest one here. These are gonna be your weakest ones up here. Okay? So your electron, well, actually just stay within a period. Okay, because here it's gonna be smaller. So that's gonna kind of play in as well. So they're gonna kind of counterintuitive to one another. And it's got a higher electronegativity. So just stay within a period. That's all you're gonna have to be able to compare. Periods and groups. Okay? That's all you're gonna compare. And we're gonna look at some in the book here in a second. All right, so that's the two trends. This is the most important trend. This is what we look at first. This is gonna be the most common thing on that trend for binary acids. Now, the other type of acid is what?
Oxyacid.
So what do oxyacids contain? And some other nonmetal. Okay? So number two, oxyacids. Okay? It's going to be HOX. Now X can be a polyatomic ion as well. Okay? So this is any acid that has oxygen in it. Okay, so when we look up here, any of the polyatomic ions that have oxygen, you put a hydrogen in the front, it's an oxyacid. Okay? Now, there's several things that we have to look at with an oxyacid. The first, it's all about electron withdrawing groups on these oxyacids. Now, on oxyacids, the deal is remember, hydrogen and oxygen have a thing for one another. Okay? It's where if you have hydrogen, oxygen, and some other nonmetal, the hydrogen is going to attach to the oxygen, not to the nonmetal. That's where I had the little silly saying is hydrogen is oxygen's hoe. They just kind of go together. Okay?
No, this entire thing's a whole hoax.
Yeah, that could be too. That's all about AP chemistry. I like that. That's a good dad joke. All right, here we go. So, the greater the hydrogen to, pardon me, what do I want? H2SO4. HClO4. The greater the oxygen to hydrogen ratio, the stronger the acid. And I'm going to say the more electron withdrawing groups, and I'm going to explain all this, groups on the anion, the more polar the OH bonds and the more ionizable the hydrogen is. I'm writing it, y'all can write it. Don't be all wusses. I gotta write it again next period.
Keep it up. Why are you erasing it?
Okay? So, in this case, if we want examples, HClO4 is going to be stronger than HClO3, which is going to be stronger than HClO2, which is going to be stronger than HClO. This is what somebody asked, what is the difference between the hydrogen to oxygen versus the oxygen to hydrogen? The greater the oxygen to hydrogen. Now, let me show you why. What does it mean with electron withdrawing groups? You want to make the hydrogen, the strong acid is the one the hydrogen is vulnerable. The hydrogen can be released easily, knocked off. So when I look at HClO4, well, let's just say HClO, okay? This is a polar bond. So the electron is being pulled this way, and this is becoming positive, and this is negative. Okay? But it's not super polar. I mean, it's polar, but not crazy polar. So when I go and I put another oxygen on here, now the electrons are being pulled by this oxygen and everything's going this way. So the electrons are being pulled by electronegative chlorine and the electronegative oxygens is being pulled, making this even more polar, more positive, more ionizable. This is probably a better term. Okay, I put the third oxygen on here. Now even things in 4 oxygens, now everything is pulling the electrons away from the hydrogen, and the hydrogen now is becoming much more ionizable and a much stronger acid. HClO4 is at the top of the chart, strongest acid.
So that's for the bond strength, and then it would be the opposite if it was the acidity.
Oxyacid, see the difference is between that one and this one, is that the hydrogen is on the oxygen, not on the X. So it's not about the electronegativity of the X, it's about how many things, how electronegative. Now, the part B of this is going to be the more electronegative the X is, the more electron withdrawing it's going to be as well. So dark time? The more electronegative the anion, the more electron withdrawing. Can't believe I didn't get through this. And the more ionizable the hydrogen is. Okay? Now, an example under that. If I want to compare, HClO4 is going to be greater than HBrO4, which is greater than HiO4. I'm comparing, it's this hydrogen, how easily is the hydrogen being removed? The hydrogen is what makes an acid an acid. We're not worried about any of the chlorine, any of these bonds. We're looking at this bond, how polar is this bond, and how easily is it to break that bond. The more the electrons get pulled away from it, the more positive and the more ionizable this hydrogen becomes. So since chlorine is more electronegative than bromine, if this is bromine, it doesn't pull the electrons as much. Iodine won't pull the electrons as much. So the size of the ion doesn't have anything, because this is the bond that we're looking to break, right here. We'll start tomorrow and do practice problems with these, and then we're going to be done with new material, and we'll start reviewing practice problems and getting ready for the test, which I said was, what, Tuesday of next week, right? All right, y'all have a great day.
If you like this video and you want more awesome chemistry content, be sure to like, subscribe, and hit that bell.